So Stephanie is a research scientist at the Center for Computational Astrophysics at the Flatiron Institute, and she's going to share with us some fun research results. All right, Stephanie, thank you.
Okay, cool. Thanks so much for that, Matt. Hi, everybody, and thanks so much for coming. I'm really enjoying the meeting so far, and I'm really looking forward to the rest of it. I feel a little bit like a British Bake Off contestant because I practiced this and I failed every time and didn't manage to finish within the allotted time. So we'll see how it goes. So I just thought that today I would talk to you about this paper that I've written with Greg Bryan, who is also here, and where we're studying the tails of ram pressure stripped galaxies. And this is fun. It's a fun paper for me because I got to do a whole bunch of stuff with YT, including some things that I hadn't really used very much. So my goal for the talk is going to be to try and orient you to the science questions we're asking, and then to show you how YT has helped me to answer them. So first, I study galaxies. There we go. So first I study galaxies, which are huge gravitationally bound clumps of dark matter, stars, and gas. Here's an image of 4 nearby ones. And these are star-forming galaxies. So these are kind of merrily growing. You can see gas in these images in blue, cool gas in blue. And that gas is able to collapse and form stars, which you can see in these images in red and purple. But not all galaxies look like this. Not all galaxies are continuing to form stars. And the galaxies that I study are a subset that are losing their gas, which is this fuel for star formation. And so in astronomy, we call these quenching galaxies. And so they're going from star forming to dead, where they can no longer grow their stellar mass. So in addition, we know that galaxies live in several different environments. We have the Milky Way, which has just one near neighbor. We have some that live like way off in the boonies, totally isolated. And then we have some that live in clusters, which are gravitationally bound groups of hundreds or thousands of galaxies that are all orbiting near each other and interacting. And this is just a nice image of the Hercules galaxy cluster. And we've found that a large fraction of galaxies and clusters tend to be these dead galaxies that have stopped forming stars. And a lot of them don't have any gas, this fuel for star formation. And maybe part of this reason is because of a lot of these gravitational interactions that can be going on as these galaxies are orbiting and near each other and interacting. But galaxies aren't the only thing, only baryons that are in clusters. There's also the intercluster medium, the RHytHM. And this is hot gas that's gravitationally bound to the cluster. And it can't cool quickly to form stars, and it can't escape the cluster potential. And so galaxies are actually orbiting within this bath of the ICM. And of course, the stars in this galaxies don't really care about this diffuse gas that they're moving through, but the gas reservoir in the galaxy certainly notices that it's moving through this higher density medium. And so it's just like when you are riding a bike, you create your own wind. This is exactly what happens as a galaxy orbits through a cluster. And so, you know, if you were wearing a baseball cap instead of a bike helmet, which is I'm a proponent of, if you were biking fast enough, your baseball cap could fly off your head. And this is what can happen to the gas in a galaxy. And we can actually see this in several cases. Here's one of the most famous, in fact, it might just be the most famous ram pressure stripped galaxy right now, ESO 137-001, which is a galaxy in the Norma cluster. And you can see it boxed here. And what we're looking at is all of the hot gas. And so this huge clump that you can see is the intercluster medium. And you can see this galaxy plunging into this intercluster medium. And you can even see this tail of gas being stripped off the galaxy. And so this mechanism that I've been talking about is called ram pressure stripping. And so this interaction between the gas in a galaxy and the gas in the cluster can remove this gas as it's kind of left behind by the orbiting stars. And there's a few, many actually, really dramatic examples of galaxies being stripped by this mechanism. And here's an example for 2, where I have some numbers written down for NEX. Longer than the galaxy disk. So here you can see this galaxy disk, which is like 10 kiloparsecs, and this huge long tail that's 10 times as long. And again, here's ESO 137, our super famous galaxy, with a very long tail. Now, actually, ESO 137 has something else really cool going on in its tail. You can see a few different colors in this tail. Blue is looking at kind of hot gas, and red is looking at slightly cooler gas. And you can actually hopefully see some like red circles in this image. And those red circles are actually showing us spots of star formation within the stripped gas in this tail. And so this is really cool. Time has passed now, but relatively recently been noticed. And so
Stephanie, I'm sorry to interrupt. Your audio's getting a little glitched out. Do you want to try shutting off your video just to see if that improves?
Yeah, thanks.
Thank you.
Let me see if I can do that.
Actually, I can do it for you. Oh, there you go. Perfect.
Okay, great. Hopefully that will help. My internet has been a little glitchy lately. Okay. So this question of star formation in the tail kind of leads to a lot of really interesting questions about what kind of gas is actually stripped off of a galaxy, what happens to gas that's stripped off of a galaxy. So only really dense molecular clouds can collapse to form stars. And it was often kind of just thought that dense molecular clouds couldn't be removed from a galaxy disk. And so is really dense gas able to be moved from a galaxy disk? Is slightly less dense gas being removed and then collapsing within the tail? And at what kind of densities is gas collapsing versus being heated and mixed into the surrounding medium? And so those are the kind of questions that we wanted to get at in this paper. And so to do that, we used ENSO, which is a grid-based hydrodynamic simulation code. And using this code, we modeled individual galaxies in wind tunnel simulations. And so we looked at an individual galaxy, and rather than model its orbit through a cluster, we just kind of blew a wind through the galaxy to mimic what that galaxy would have felt along its orbit. And so first we can kind of take a look. Oops, I keep on pressing the wrong button. We can take a look at the simulations. And so, one of my favorite things to do is to just take a look at a projection plot. Here I'm taking a look at a projection of the density, and I've just kind of cleaned it up. So I'm only looking at kind of the interesting section of my simulation that's near the galaxy. I like the color map magma. And then I annotated a whole bunch of lines, which I'll talk about in a minute, and then some text so we could kind of follow the time of the simulation. And then once I make all these plots, I just tack them together using FFmpeg to make a little movie. So let's see. Uh-oh. There we go. I clicked it twice. So you can see gas is being stripped off here. And you can also see lots of clumps of gas in this tail. that are moving away from the galaxy as they're blown off by the wind. And so what I want to do is I want to try to understand, what's driving the acceleration of this gas, and what's happening. Is anything different happening to really dense clumps versus more diffuse gas in the tail? Well, as I mentioned, ENSO is a grid code. And so that means that gas is moving through a grid. And so even though we're seeing kind of these clumps, I can't follow an individual parcel of gas within ENSO. And so instead, I looked at kind of the gas properties in these thin regions at different heights above the disk. And so I identified, clumps in these simulations. And so I looked for clumps here using level sets. And actually, all of these lines of code are mostly here just so that if I post this, you all can follow along. But this is like directly taken out of the YT cookbook. So kudos to the YT cookbook here. All I did was I selected this region with data source. And then within that region, I said, I want to look for regions of high density. So that's where I define my field. And then I set a minimum value of 10 to the minus 26 in CGS units. And then I stepped up in factors of 2 to try and look for more and more dense regions. And when I do that, I can then project and annotate all of these clumps. And so this is one of the snapshots from that movie. And this is a lot of clumps. This is like 700 clumps in this tiny region. And so now you're getting kind of an idea of why I went with the tiny region. This is a super memory intensive process. And, sometimes I got up to, more than 2,000 clumps in this region, and then my computer would run out of memory. So I used pretty narrow regions. And then I kind of saved a lot of information about these clumps into a file. I saved the mass, the number of cells in each clump, and its velocity, temperature, density, metallicity, so that I could really try and dig into what's going on in these clumps. And then I said, okay, well, do clumps move differently than the diffuse gas in the tail in these regions? And so we came up with a model for how gas would be accelerated. And we said, okay, mixing is really what accelerates gas. Mixing with the ICM is dumping momentum into the gas. And so I can come up with this model of amount of mixing and velocity in the wind direction. And that's this black line here. And then I said, okay, well, I actually want to compare that with what's going on to the gas in the tail. And so I said, okay, in that narrow region, let me plot the velocity and annotate with phase plot. And so you have to use create profile, but it actually looks quite similar to
Stephanie. As a note, you have 6 minutes till the end of your slot.
Great. Okay. So wow, I'm slow. Okay. So I defined a variable and I plotted this, and this was all so that I could kind of plot this model line. And then I also just added some text so that I could follow along. Okay, so then I did the same thing with my clumps, and that wasn't in YT, so I'm not going to show you how. And look, they fall along the same model line. So all gas and clumps seem to be accelerated in a similar manner. So clumps aren't these really like dense knots that are being pushed. They're just like all the rest of the gas. Okay, well, let me compare some different winds. What's going on? Because I wanted to know, does the wind matter for mixing? When does gas cool? What's going on with clouds? And so then I said, okay, I need some volume rendering to gain some intuition. And this I thought was pretty shocking because I almost never use volume rendering, because usually I just think it's, for making a cover on the science magazine, not for actually doing science. But I think that you'll see that these volume renderings give a little bit of intuition. And so I created this transfer function that highlighted the densities of the clumps that I was looking at. And then I have a movie of my volume rendering. And so this is the simulation that I've been showing you all along. And you can kind of see that with this volume rendering, I'm highlighting these little clumps in my tail. And maybe as you move along, you can see that I'm getting kind of fewer clumps in at larger distances than nearby in this tail. Okay, so maybe in this simulation, there's kind of fewer clouds the farther I go. Now let me up the density of the wind and keep the velocity the same. And when I do that, I again still see these little loopy clumps, but I see some pretty dense gas, this blue gas, existing high up. And so I actually think that maybe I'm seeing that clouds are accreting gas and getting denser and more massive as I go farther from the disk. So, okay, now let's do the next step and say, okay, now I have high density, let me go to high velocity. And here's where things get really cool in the volume rendering, I think. Whoa, okay, so when I've upped my velocity, all of a sudden my clouds don't look like beautiful little loops anymore. I can totally see in this volume rendering that they are getting absolutely shredded here. And so, you know, if I continue this movie on, you can just see that these clouds are shredding right into the surrounding medium. And so, you know, I actually was able to get some physical intuition with volume rendering. And then what I did was I said, okay, well, can I actually measure this growth? And so I did some regions, some disk regions, and then I only looked at the dense gas in these regions. And I said, okay, what's happening? Is dense gas actually growing quantitatively? And so for that, I just, you know, looped through everything and summed up the masses. And then for each of these, I plotted, this is kind of a busy plot, so let me highlight what I want you to look at, the dense gas in the wake. And I can actually see that the dense gas is declining in those two cases, low density, low velocity, and high density, high velocity. But it's increasing as in that high density, low velocity case where we thought we saw maybe some growth in the volume rendering. So anyway, so my take home points I can just leave up, which is Clump Finder is a really neat tool that I think could be of use for a lot of hydro questions. You don't have to use density in the Clump Finder routine. Phase plots are the best plots. Volume rendering can actually be really useful for giving some physical intuition in addition to being really pretty. And other than phase plots, cut regions are the best thing about YT, in my opinion. So thanks. Sorry I was long.
Thank you very much, Stephanie. So I would like to open up the opportunity for folks to ask questions. Remember to use the hand raising. We only have a minute or two. Yeah, Ryan.
Hi, Stephanie. Great talk. It's really cool seeing the different volume rendering movies. So I guess this is a little bit more of a science question than a visualization question, but in terms of doing your clump analysis and all that, were you able to look at like if there was a radius dependence on which clumps ended up growing in the case where they did grow versus if there were other clumps that ended up still being destroyed even in the case where you overall saw growth of dense mass?
Yeah, so we tried to look at kind of individual clump properties. You know, we're pushing the envelope a little bit in this simulation. So Clump Finder can actually, you can set these validation parameters. So I could have within Clump Finder said like, I only want clumps that have a certain number of cells. I didn't do that. I did that in post-processing. And I find very similar trends, whether I say, I'll allow clumps with only 10 cells versus if I say, no, I need a clump to have 300 cells in order for it to be called a clump. And so I find pretty similar trends, although, you know, not surprisingly, 10 cell clumps do tend to get more destroyed than 300 cell clumps. I don't know if that answered your question, but we could talk more on Slack too.
Yeah, sounds good. Thanks.
Thank you. So Cameron also has a question, and then I think we have to move on.
Hey, Stephanie, great talk. I just wanted to ask, and you may have addressed this, I had to jump out for a second. Did you look at the resolution dependence in the simulation on what the properties of the clumps were? Because I know when I tried to use it in the past, there's a super resolution dependence, but most of the clumps that I was dealing with were going down to the resolution limit of the simulation, but I wasn't sure what your experience has been.
Yeah, so we're actually doing that test right now. So this is a paper that you will not find on the internet or on the archive because we are still in the referee process and doing some of these last tests. Yeah, I do still find some clumps. But yeah, I mean, the properties are definitely different in these different resolutions. I mean, it's really interesting to kind of see even just the distribution of clumps within the tail differs with resolution. So yeah, I think the general trends are going to hold as to like what tends to be destroyed, what tends to survive, but like numbers and masses, no way is that going to hold with different resolutions.
Okay, cool, thanks.
Awesome. So I think we need to move on to Michael Meehan's talk.